Okay, so what I'm going to talk about is Bootstrapped or self-hosted ClojureScript and how that works in Planck. So to start off with, I kind of have this picture that helps me understand the difference between just regular ClojureScript and Bootstrap ClojureScript at least from a very high level. And if any of you have questions while I'm going through this, feel free. I can try to delve into things that aren't clear. But one way I kind of look at regular ClojureScript is you basically have your application code, and that's this box up there. I don't know if you can see my cursor. Okay, and the way I kind of view it is you have your application code, and you also have essentially the core library, if you will. And that's what this core cljs is. And you pass them through the compiler to emit JavaScript that runs in your environment. And I represented it as separate files, but usually you take that JavaScript and you pass it through Google Clojure to minify it, especially if you're going to target the browser. But the main thing for Bootstrap ClojureScript is the fact that the compiler in ClojureScript is written pretty much entirely in Clojure. So there's always been this thought like, hey, can you take that Clojure, which is pretty portable, and can you compile it as ClojureScript, as if it were ClojureScript? And for the longest time you couldn't, because truth be told, there's things down in the compiler that are JVM based. But this is what Bootstrap ClojureScript ends up looking like, at least from a really high level. And the difference between this picture and the previous one is now at the top, the compiler itself is being passed into the compiler. And that's kind of the mind-bending thing. The compiler is able to compile itself. And it essentially results in the compiler appearing in your JavaScript evaluation environment at the bottom. And what that effectively means is that if you have ClojureScript code that's available to this environment at the bottom, you could pass that ClojureScript code through the compiler that's now essentially in JavaScript, and it would emit new JavaScript that represents that code. That from a high level is roughly what it looks like. And you essentially have, if you look at this bottom part here, you no longer have the JVM involved. You're able to just compile all by yourself. And I think the reason it's called bootstrapped or self-hosted is this idea that the compiler is compiling itself. But you get the JVM based one, I would say, for what you're conventionally dealing with, but it has built within it now the capability to do all this stuff. And I'll actually give you demos of that. So if you were to download something like Planck, for example, you're getting the bottom thing. You're getting Bootstrap ClojureScript alone. But to answer your question, if you just go and download, like you get Figwheel or whatever, or just the cljs jar that ships with ClojureScript, that's the JVM-based ClojureScript. Exactly, yeah, that's a good observation. If I go back a previous slide, this is a CLJ file right here, if that's what you're referring to. So the compiler, in order to make it portable, and I'll show a little bit of that, the compiler had to have some conditional code put into it to make it so that it can be compiled as ClojureScript. Yeah, I mean, if you just looked at if you looked at this comp CLJ file, if you looked at it if you go back a year and a half ago before any of this occurred, you would see that it's a bunch of Clojure. But if you look closely, you would see JVM interop things in there, like throwing exceptions instead of JS error. Little things that are truly JVM specific. I don't know if that answers your question. We'll get to some examples later on, and you might get a better sense of that. Yeah, exactly. Yeah. Okay. So in my next slide here, I think I was starting. You guys are saying, how did you do this? And that's what my next slide was: is how did you pull this off? How was this done? And the first thing I was alluding to is that the compiler is the ClojureScript compiler is written in Clojure essentially. If you look at the Clojure compiler, there's a lot of Java in that thing, right? But if you look at ClojureScript, that compiler, I would say they took a fresh start, and it's all written in Clojure. And David Nolan did a count recently and found that it is pretty much, there's like a tiny bit of JavaScript in there. And I can attest to this because I've been contributing pretty heavily to the ClojureScript compiler, and I don't know JavaScript at all. So it's all just Clojure. And what Alex was referring to is this reader conditionals thing right here. And by the way I understand things myself is by way of example, and the bottom here shows a small bit of code from the analyzer part of the ClojureScript compiler. And this small example code here is basically the handler that, it's basically the thing that gets called when an error occurs when it's analyzing your code. So for example, if you try to, in ClojureScript, if you try to use a var that hasn't been defined, this method will be called, and it's going to print something on your screen and say, hey, warning, you're trying to use a var that hasn't been defined. And clearly, in Clojure, you have an out stream and an error stream, the JVM specific things. And those don't exist in ClojureScript. ClojureScript is not the JVM. So this is one very easy thing one easy example to understand where you kind of need a little bit of conditional code to do something slightly different if you're going to compile this code as ClojureScript. Some other conditional code in there is little things like I mentioned before where the code needs to throw an exception. So instead of throwing a JVM-based exception, it may throw a JS error. There's other things in there that are done for performance reasons. Like one example is there's in ClojureScript there's this way to compare keywords. You can use keyword equals to compare them instead of using the equal sign operator. Those things I would characterize those as just being optimizations. So that's why, if I go back to the previous slide, that's why the compiler is cljs. If you look at it, it's pretty straightforward, but sprinkled all throughout it now is a bunch of conditional code to handle fairly straightforward differences that you need to have. Okay, so I want to give a demo of what it looks like to actually use this thing. If you download ClojureScript, there's this low-level cljs jar that you can get directly from the GitHub repo. Most people don't use this, but most people end up, I think, experiencing ClojureScript through Figwheel or some higher level thing. But if you want to, you can get this low-level jar, and you can start up a ClojureScript REPL by just running it this way. You have to have Node installed to do it this way. If you don't have Node, you can change this last ending bit here to say Nashorn, and it'll use that JavaScript environment that comes with Java. So this will start up. This top part just starts up a ClojureScript REPL, and then what I'm going to do is require this cljs.js namespace, which has the it's kind of like the API to Bootstrapped ClojureScript. And then I'm going to evaluate this expression at the bottom here, which is going to basically take this string here and essentially compile it within Node. It's gonna use the ClojureScript compiler that's inside a Node to read that string. First of all, there's going to be the reader involved. And that was on my, I guess I skipped that point on my previous slide. The reader has had to be ported over to ClojureScript as well so that you can actually read on that side. It'll read this, and then it will it'll basically compile it and convert it into JavaScript, and then it's going to pass it back to me, essentially calling. It's basically going to call this JS_eval function, which essentially you could basically say that function tells the JavaScript environment to evaluate the resulting JavaScript. It's no more complicated than that, and I think I wish I had this to show this to you, but it's really I think it's a call to just tell the JavaScript environment to do exactly that. But you have control in terms of how you want to choose to evaluate things. And then this context expression basically is kind of telling it how to treat this thing. It's basically saying, hey, this is an expression as opposed to a statement or something else. Usually, if you imagine creating a REPL, almost everything you type into a REPL is basically expressions. And then after all that's said and done, the last argument to this is a callback, which is a handler that it'll basically call back upon you with a map that gives you the results of all that. And that's one thing that's kind of different with Bootstrap ClojureScript is the entire thing is asynchronous. So let me demo that. I have my little cheat sheet here. Okay, so I'm going to start up, like I said, I'm going to start up a ClojureScript REPL using the shipping version of the cljs jar. So if I did, we're now in ClojureScript, and that's the version that we're in. And we'll require the API to Bootstrap ClojureScript, and then I'll evaluate that thing that I was just now talking about. So what it gives us is, of course, what we wanted. The number 3 comes back out, and it comes in a map so that it can also tell you. Fundamentally, you could also get an error back instead of this map here with values in it, and that would help you if something was wrong. And it also tells you what namespace you ended up in after evaluating that expression. And that will become clearer in a little bit later on. So that was pretty long-winded. I don't know if that whole thing made sense, but at a high level, that's roughly that's a kind of the smallest example you can give of using Bootstrapped ClojureScript to compile a string, evaluate it, turn it, Yeah. Okay, yeah, that's a good question. So fundamentally, we need some JavaScript engine if we're going to do this at all. So you can use Bootstrapped ClojureScript in any JavaScript engine. So you could imagine this being in a browser. So I just chose to do it in Node. Yeah, that's all Node is there for. I could like I said, I could change this to Nashorn, and that would be that JavaScript engine. As a matter of fact, with Planck, it's JavaScript Core. It's another JavaScript engine. So I think that answers that question. It's just a JavaScript engine. Okay, so what this example was making use of is this cljs.js namespace, which I think is poorly named, but people were voting on what to name that namespace, and that was the best that anyone could come up with. And at a high level, what I was showing was eval string. There's also, if you have a form that's already been read in, you could call eval. And these things on the left here are kind of the high level things that I think that API offers is these 4 things. And so eval essentially will call upon compile, and that actually makes use of analyze to even do that. And require is all about loading other code into your environment. So to be honest though, most people I think stick down near the bottom with just eval, unless you're trying to write something else that's perhaps compiling code and emitting the JavaScript for some of the. Okay, so if you look at the ClojureScript compiler, it's roughly broken up into 2 large chunks. There's the analyzer and then the compiler, and the analyzer, I would say at a high level, basically looks at your code. It analyzes your code and essentially forms this gigantic map. It's like a gigantic AST that is a representation of the result of the analysis of that code. So it knows the structure of your code. It learns what the symbols are. It resolves them. If there are macros in your code, that's the point at which macros get expanded. And I'll actually show a little bit later this thing called the analysis cache that has a lot to do with what analysis is all about. So let's see. So one question I have is, do we even need this API? Why couldn't we just use the existing API that ClojureScript has? And I think, partly you don't need it. And I know you don't need it because things like Replete and Planck and other things existed prior to cljs.js existing even. So you could fundamentally call on the lower level things yourself anyway. But I think the reason it came into existence is because it needed to be asynchronous, and it's different enough from the regular ClojureScript APIs that it just kind of made sense to put a lot of the Bootstrap specific stuff into a certain namespace, and that was kind of a nice landing spot for all that stuff. And a couple of things also to know about, to be concerned about if you're going to use this, is once you require cljs.js, your application becomes much bigger. It's huge, because what you're really doing is you're essentially bringing in the entire compiler, and you're also bringing in the entire analysis cache that goes with the core library that goes with that. So those things, I think they can double your executable size. So you wouldn't want to just include this in a web app unless you really were going to use it. Because another problem is you can't pass this stuff through Google Clojure, so it can't be minified. So once you use it, that's another contributing factor, is it's going to be in its non-minified form. So it's a pretty significant debt to take on. But one thing that's kind of interesting though is David Nolan was looking around at Google Clojure, and he noticed that somewhere deep down in there they have a translation of it to JavaScript. I don't know how they did it. Maybe it's GWT based or something like that. But it basically opens up the idea that maybe all this Bootstrap stuff could be subjected to Google Clojure optimizations, and then you could essentially, if you wanted to, build an entire ClojureScript compiler that doesn't use a JVM at all. And like you could today, but what you would be missing is the minification. But with this discovery that you have Google Clojure available in JavaScript form, that lets you, it opens up the idea that you could do this. So maybe another year from now, we'll hear that someone else has tackled that, and we have like a pure JVM free compiler. Yeah. There might be, yeah. So that's one part of since I've been for the past year or so, I've been messing around with Bootstrap, and so I have not dealt with the Clojure compiler aspect. So that's one area of that entire code base that I'm not too familiar with. But I wouldn't be surprised if you could just take your stuff and have it minify it for you. Okay, so I think it's the whole Bootstrap ClojureScript thing is not really it's not really in part of any normal ClojureScript workflow right now. You like, in order to work quickly, you have conventional REPLs today that allow you to do that. Bootstrap ClojureScript lets you do things that you couldn't previously do. Like you can now bring the compiler with you into the target environment, and you can use it there. So if you have a use case like that, it fundamentally lets you now consider doing things like that. And I have some examples of uses of all this stuff later on to give you some feel for what the kinds of things that people have built with this. Yeah, you could. I mean, it's you could imagine, like entire IDEs that run on iPads now, because you could almost do anything now because of this. It's just up to your, how much work you want to put into it and your imagination. It's possible now. So this next slide, so what I had in the previous example that I showed in the demo, it essentially involved evaluating arguably just a single form. And this is an example of what happens if you evaluate this like a namespace form. And what that essentially means, what it's all about really, is loading other namespaces into your environment. So if you do evaluate something like this, what you then have to do is make sure that you have a load function defined. In that previous example, I did not define a load function, and everything was okay because it wasn't needed. But if you do this, if you require something, you need to have a load function defined. And what will happen for this specific example is that load function will be called with two arguments. One of them will be a map that looks like this. That basically tells you the name of the namespace that needs to be loaded. So in this case, bar core, whether or not it's a macros namespace. Because we're just requiring it, like we're not doing require macros. This is a falsy value here. If this were true, then you would have to satisfy the load function by loading a macro namespace instead. And it gives you a hint, I guess, a path as to where to load the code from. Now, you can choose to, like if you were building an IDE, you could choose to load this namespace from disk. Or if you were doing this in a browser, you could fetch the code across the wire. So that's part of why all this stuff is asynchronous as well. I think it has a lot to do with this load function needing to be asynchronous. And when you're going to call back upon the callback in order to satisfy the load function, you pass back a map, and in that map you pass back a keyword telling the compiler what the language is that you're about to pass back. Normally it would be ClojureScript. You're passing CLJ is the keyword that means ClojureScript. But you can also pass back JavaScript. And that's useful in the case where you have a namespace form that is importing JavaScript code. And in that case, you still need to essentially load it, but what you're passing back as source is now JavaScript, because you're basically loading a native library, if you will, or a foreign library. So let's see. I want to give an example of this thing. I think this is probably the most complicated example in this presentation of how to use this stuff. So this is like the previous one. It's evaluating a string, and in the previous one, I had a simple form that was adding 1 plus 2. I think in this case, it's just a namespace form, and here's that beast, that load function. And what I'm going to do in the demo of this one is to kind of give you a sense of what it's doing. I have like a little poor man's debugging print statement right here to print out this map that's going to be passed to it. And the source that I'm passing back to it is a little bit of source that itself does a side effect by printing to the screen. And if you think about it, that's when you load code in ClojureScript, really what you're doing is you're causing the compiler to sequentially go through those forms that are in that namespace simply for their side effects. You're basically having defs be evaluated, which are side effectual, and in this case, my side effect is going to be a print of this keyword bar. So I have my cheat sheet for this one here. It's too much to type. Okay, so can you see this thing here? I guess this is big enough for you. I can make it larger if it's not big enough. So in this case, all right, so like I said, like I had in the slide, you get called with this map. That's what this PRN here called. And it basically showed that we're basically being, my client code here is being requested to load this namespace or provide the source for this namespace. And when I did that, my code passes back this string here. And what happens is inside the cljs.js namespace, it essentially takes that stuff, compiles it, and evaluates all the forms serially. And part of a consequence of that is that this bar prints here. And then when all is said and done, it calls my callback, the PRN here, and that's where I get this map coming back out here. And previously, the value that I got was the number 3. In this case, the value of an NS form is nil once you evaluate it, so you get back this. And of interest here is that the namespace that I'm now in is the foo core namespace. Now, if you see here, I'm still down. I'm actually in cljs user in my JVM based REPL, but this would be if you were when I show you actual Bootstrap REPLs like Planck or Replete or any of these, you would then essentially your REPL would need to look at this symbol here and record it and say, okay, I now need to be in that namespace. So that's roughly the two high level ways to interact with the cljs.js namespace at that level. And okay, so this slide here is just kind of showing, this is just a fun fact. In Clojure, there is, I think this is true, in Clojure there's a require function. I think that's what it may be in Clojure. In ClojureScript, there's actually no such thing. there's no require thing, but you can type this in a REPL. You can type this in your ClojureScript REPL, and what require ends up being is actually, I would call it a REPL special. Just like there's special forms, like if, require is a special form, if you will, that's only known to the REPL. The REPL sees that form and says, oh, I know how to deal with that. And what most REPLs do in response to a require is they quickly convert it to an NS form that looks kind of like this. And so what this does is it basically keeps you in the namespace you were in, but it has a side effect of loading the foo core namespace. And there's other little bits of complexity surrounding this where, like, if you were to require foo.core, but then later required it again and gave it an alias, you could say require foo.core as foo maybe, and then maybe even gave it another alias as bar or whatever. What has to happen in a REPL is those aliases have to be merged together. So there's actually extra, if I remember correctly, there's extra meta that goes with the namespace form to tell it basically asks the compiler to merge these things together, essentially to preserve your previous things. And if you're kind of new to ClojureScript, one mistake to make is to actually load a namespace by calling ns. And what that'll do is it'll blow away all your aliases and stuff like that, because what you really need to use is the require, because it preserves a lot of the stuff. But anyway, that I guess this whole conversation really has not much to do with Bootstrap, but it's just kind of an interesting factor of the way REPLs work. Okay, so the analysis cache is so in those previous examples that I gave, the first argument was this thing here, cljs.js empty state, and from the big picture, what really happens when you load ClojureScript code and evaluate it and compile it, there's roughly two things that occur. One thing that's pretty obvious is that all that stuff gets turned into JavaScript, and that JavaScript gets evaluated in your environment, and that JavaScript itself has side effects. It defines new JavaScript functions and stuff like that. But another huge side effect is the fact that the analysis cache gets changed, or the result of analysis gets captured, and this cljs.js empty state is actually an atom that you can think of. You can essentially mutate it. You can add new things to it. So one mistake a lot of people make when they first start using Bootstrap ClojureScript is to always pass the same argument in again and again. And essentially what that does is it passes in an empty analysis cache. So for example, if you define a function and you try to then go and use that function in Bootstrap ClojureScript, if you pass the empty state in again, you'll find that function's not there. Actually, I have a demo of that. I think a demo will kind of make all this stuff kind of clear. Okay, so this is, like I said, I'm passing in an empty analysis cache, and my code is going to have a side effect. It's going to define x to be 3, and what that's going to do is it's going to mutate the JavaScript environment to set something to be 3 in there, but it's also going to actually introduce this var x. So if I do that, I get the var back x as a result. But here's the key bit. This is the mistake that a lot of people make. I'm going to try to use x. I'm going to try to evaluate x, but I'm going to pass in the empty state again. And when I do that, this kind of illustrates what I was just describing, is that the compiler, if you will, doesn't know what x is because I passed in the empty analysis cache. You get the value 3 back out because half of the side effects did occur. They actually happened in the JavaScript engine. It's really just a problem of the analysis cache lacking that information. So to make a long story short, the way to fix this is to basically define your own var to hold that mutable atom. And if I run through this again, but instead pass in my st right here, instead of passing in empty state each time. Now, when I do that, I actually will get the same answer back, but I'll avoid the warnings, because in order to evaluate this, it was able to look it up. It was able to consult the analysis cache. And here's a thing that will show you what's in the user namespace portion of the analysis cache. Just to kind of give you an example of what all this is really about. So this is basically saying things like the fact that, let's see, well, you can see things in here. Where is it? There's a def in the cljs user namespace now that has the symbol x. And if I were to define a function, you would get things like the number of arguments. So that's how, like, if you were to call a function with an incorrect arity, that's how the ClojureScript compiler knows that you're even doing that, is through the ability to do analysis and consult this analysis cache and see that the arity is incorrect. So that's to summarize all of that long-winded story there, is that you basically need to consider the fact that the analysis cache is a big portion of the state, if you will. Okay, so let's see. All right, this bullet point. Oh, geez, sorry, I can't click on this. So calling code in your ambient environment. What this means is, if I were to in my demo, if I were to define some functions and in the JVM side of things, you'll find that those aren't automatically visible to the Bootstrap side, simply because they're not in this analysis cache. They're not available in the sense of analysis, but like we just showed, you can sometimes just see them anyway because they're in the JavaScript environment. So that's there's an example later on that I'll show you called Klangmeister that involved this ambient environment issue. So this analysis cache is, it exists for CLJS core. So every single function that is in there, when you call it, that's how it knows that you're getting the arities correct and all that kind of stuff. And this analysis cache is huge for CLJS core, just because that library is huge. It's a lot of functions. And if you use it by default and it gets encoded as Eden, by default, that is extremely slow to load in. So what you can do is you can consider, if you're actually building a solution that needs to perform well with Bootstrap ClojureScript, you can instead use transit. And I think actually ClojureScript itself just recently, it's actually still in master, but it's switching to using transit for its own analysis cache. So if you are compiling regular ClojureScript code, there's this output directory that it writes stuff to, and in that output directory is a bunch of JavaScript and also analysis metadata information, and that's being switched to transit for performance reasons. But the main point of this bullet here is that for Bootstrap, that analysis cache of that guy is huge, and if you if you want to make it go even faster, you can consider lazily loading parts of that analysis cache in. And I'll show you how Planck did that. I won't show you how, but I'll show you the effect of it later on. So macros. Someone asked about macros. So one misconception that a lot of people have about Bootstrap ClojureScript is that macros don't work in Bootstrap ClojureScript, that they don't exist at all. But they do. You have to write your macros in a way that they can be compiled as ClojureScript, and that's because that's what you have is a ClojureScript compiler available to you when you're in Bootstrap mode. So if you're going to load a macro file dynamically, there is no JVM based. There's no Clojure to speak of to compile that macro file. So you have to kind of write your macros in a clean way so that they can be compiled as ClojureScript. And one thing that's kind of weird is that the macros, even though I just said they have to be compilable as ClojureScript, they still go in a CLJ file. Or if you can put them in CLJC files if you have conditional code that you need to have in your macros. And let's see, the reason for the CLJ file stuff. There's this philosophy or stance that I've seen David Nolan take, and I think it's coming from him and Cognitect. And the idea is that I think the best way to say it is that they don't really want to see Bootstrap ClojureScript become a wholly separate thing. And it arguably is. The fact is it is a separate platform or target, but they don't want it to become this, like the burden of this third platform to support. And really they want to make it so that there's a good chance that you can actually successfully use existing ClojureScript code in Bootstrapped environments. So one consequence of that is, like I just mentioned, your macros still need to go in CLJ files, even though they're going to be compiled as ClojureScript. And if you do that, then your macros arguably could be used by regular ClojureScript as well, because they could be compiled as Clojure. And this actually is working. Some examples of some libraries, like there's the Markdown CLJ library that existed well before Bootstrap ClojureScript, and it supports ClojureScript, but it in fact also works out of the box in Bootstrap ClojureScript. I would say simply because the code in that library is fairly straightforward and fairly clean. It's not using Java interop to implement its macros. They're fairly simple and clean. And Spectre as well. I was looking at that code, and I mentioned to Nathan Mars that he could actually support Bootstrap ClojureScript if he were to just change one line in his code, because he was using, there was one spot where he had like a use form in one of his macros, one of his namespaces. And if he instead were, ClojureScript does not allow you to use the use keyword in your namespace forms. And he switched that, and then Spectre became, available to Bootstrap ClojureScript as well. Now, since then, Nathan Mars has gone off and changed Spectre even further. So he's had to go make more changes to make it compatible with Bootstrap ClojureScript. But that's an interesting, it's a pretty sizable library that I thought was pretty cool that it was actually usable in Bootstrap ClojureScript outright. And I think that's because of this philosophy, like trying not to make things too different. Another one that does not work out of the box is core async. And that's because that to me, that's like, the mother of all macros. The Go macro is the most complex macro that exists in the world, right? And so I ultimately was able to get it to work in Bootstrap ClojureScript, but the changes were so complex that I don't want to submit them back to the mainstream core async. So I've kind of forked it, and I have a library called Andare that I'll demo later on. And TestCheck is another library that does not today support Bootstrap ClojureScript, but it's like there's like 5 lines of code that need to be changed in it to make it so that it can run in Bootstrap. So that's what I'm kind of finding, is that if you ignore core async, which is its own problem child library, if you look at all the other ClojureScript libraries out there, with a little bit of porting, you can kind of clean them up It kind of reminds me back when we were switching from like 16-bit to 32-bit code, and you had to make sure that your pointers were clean or whatever. With just a little bit of cleanliness, you can get your libraries to run on these two platforms. Yep. Yeah, I'm with you. I mean, it's the whole macro thing is a mess in my opinion. You know, it's you have this beautifully simple language, and then you look at the macro story, and it's a big mess, right? It's really complicated and really hard to deal with. And Bootstrap ClojureScript does indeed open the door to possibly letting you clean up some of this stuff. And sometimes I'm finding that some things actually end up being simpler when you're in Bootstrap ClojureScript because of the fact that you have everything there with you. I kind of think that if you look at what ClojureScript did was it optimized for a certain use case, right? It wanted to really cram stuff into a browser. So it really, the form that it took reflected that use case by separating out macros and all this stuff, just to make it fit that particular use case. And then you go and if you mess around with Bootstrap enough, you start to see that, things become kind of more uniform and a bit more like Clojure, or they could be more uniform. So I agree with what you're saying. And it is horrendously complicated to try to build a library that is portable across all these things. And it's hard to read that code. So this kind of speaks to part of that. Even though like Bootstrap's ClojureScript it kind of opens the door for you being able to do what you see occurring in Clojure, where you can have, you can define a macro and then you can call it from a function in that same namespace. This does not work in Bootstrap ClojureScript, and it's intentionally not supported because if you were to do that, then you would end up writing code that would not work in regular ClojureScript. So Cognitech / David Nolan is not interested in supporting that mode, but he's said many times that there's nothing to stop anyone from going off and doing it themselves, and it would in fact work. And this fourth bullet down speaks to, I guess, some of the complexity. If you try to define what are the constraints of macros now, previously you could make this statement that's scratched out here. You can say, well, macros are just Clojure. They go in CLJ files, and when you expand them, they have to take they have to target the capabilities of ClojureScript. That was the story, and we all got used to that. Now with Bootstrap, things get to be a little more complicated. And you have to, we kind of struggle to come up with a good, clean, simple definition of what are the constraints on macros. And this is the one that exists right now, is that they have to be in a different compilation stage. I think David Nolan came up with this term from Racket. I think they used the term stage. That's where this came from. But what it essentially means is if you imagine the compiler compiling, if you're going to use a macro, it essentially needs to roughly come from another namespace. That's one hand-wavy way of saying it. And so you could imagine like a tower that results from this. You have like a macro in a namespace, and then that macro needs to call another namespace. So you end up with this tower of macros. But in fact, those towers can collapse because at expansion time, if the expanding site ends up, you can end up with macros that look like they're calling macros in the same namespace, but they're not calling it because of the delayed nature of expansion. So you end up with the ability to put. It's not as, I guess what I'm saying is it's not as bad as it sounds. You can end up with macros, especially if you have them inside a syntax quote. They can look like they're calling macros in the same namespace. And then you can have this other weird thing that's like a loop, where you can have a CLJC file that is a namespace that includes itself, and for the purposes of the macros in that namespace. And that's just weird, but it works. That's fundamentally how parts of ClojureScript itself works. And you end up with kind of like this loop pattern where you include yourself, and by doing that, you satisfy this compilation stage rule. where the macros you're using come from not a different namespace, but a different compilation stage. So I think all this is very complicated, and it's part of why a big part of this presentation has macros in the middle of it is because this is such a complicated subject. And to be honest, I'm still learning the corner cases of macros even still in terms of how they work with this stuff. Okay, so this is another weird thing about macros. So if you look at ClojureScript and you look at regular ClojureScript, you can have a CLJ file that has maybe a function or even a macro named foo.core/bar. And you can have the same thing in cljs. And that's all cool, right? Because they're separate. This is done in Clojure, this is done down in ClojureScript, and there's never a collision, if you will. But in ClojureScript, one thing to consider is that you can have functions that are also macros. An example of this would be like the plus function or the inc function. There exist macro versions of those in ClojureScript, and I think the reason that those macro variants exist is for performance, so they can just expand out. They're kind of like an inlining mechanism, and Clojure itself has the same thing conceptually, but it doesn't take on the form of functions and macros having the same name. And I think if you look closer, there's a thing that you can do in Clojure where you can give it some meta that says that this thing is that there's an inline definition for a function. But the whole point of all this is that you can have functions and macros with the same name, and in regular ClojureScript, this ends up not being a huge deal. It ends up not being a collision problem because of the separation. You have you have your compiler in the JVM for the CLJ part, and then the runtime stuff is in the other side, and they never bump into each other. But in Bootstrap ClojureScript, everything's all together in the JavaScript environment. So I think it was David Nolan that came up with this solution. And the strategy is to basically tack on this $ macros as kind of like an internal implementation detail of the way things are done. So internally, if you are in Bootstrap ClojureScript and you require a macros namespace, what it'll do internally is it'll turn it into this thing that has a $ macros appended to the end of it. And that effectively is enough to keep things separated. And there's like little switches all throughout the ClojureScript compiler code base to cope with this game that's being played, to keep macros in this separate pseudo namespace. But like any, this is one of those kind of tricks where, you use your own technology to solve something in this weird way, and you try to keep it as an implementation detail, but it leaks out everywhere. So I mention this because you'll see this, one way you'll see it is if you end up with like compiler errors that talk about things not being defined. You'll see this $ macros thing appearing at times. And another place where you'll see it is if you're writing macros that use syntax quote, where you if you have a symbol, like to take a simple example where you have a macro that needs to call a function, like a helper function. That helper function could be defined in that macro namespace, say above the macro somewhere. And if you do that, you can use syntax quote, and it'll resolve to that function, and it'll automatically use this internally. It'll use this $ macros thing as part of the namespace that it ends up being in when it I guess the right term is resolving to point to that function. But if you need your macro to instead call a function in your runtime namespace, down in the ClojureScript side, what you need to do instead, if you use syntax quote, if you don't qualify that name, it's going to end up qualifying internally with this macros thing on it. So what you have to do then is you have to know that what's really going on there, and you have to then qualify it with the namespace you want it to resolve to. I know this is hard to say in words. I probably should have made a slide for this. But what it means is, like, let's say you wanted to call, let's say you were in the macro namespace and you were writing a macro that wanted to call a baz function, but the baz function lived down in the ClojureScript side. You would have to qualify it as foo.core/baz, basically defeating syntax quote so that it doesn't expand for you, and put that $macro thing on it. So this is just like a little corner case. Maybe in the future this stuff will be cleaned up and taken care of automatically. But there's still some odd corner cases like this that occur with macros if you're playing around with this stuff. And I thought I'd point that out. All right, so I think that's roughly it in terms of the underlying technical explanations of this stuff. So I wanted to just talk a little bit about where some of this stuff is actually being used. The first thing that occurred was REPLs. As a matter of fact, I immediately wanted to write a REPL for iOS. I've always wanted a REPL on iOS, and this was, in my mind, one of the first times it was really easy to do that, in the sense that, I don't know if you can, but I don't think you can get a JVM onto iOS. I suppose you could put anything inside your iOS app, but really you have JavaScript core there for you. So that was the first thing I did, was I made a little REPL called replete. And then Tahmid Sadiq made kind of a similar thing for Android. So these are kind of cool. These are like little REPLs you can have on your mobile devices. Actually, prior to that, Joel Martin, he's kind of like the godfather of this Bootstrap stuff. He actually did the whole CLJS in CLJS like 3 years ago. He did a fork of ClojureScript and pulled this stuff off way back when, prior to reader conditionals. And he's now updated his stuff, his ClojureScript.net website, to use Bootstrap ClojureScript. And there's Planck, which I'll talk about in a bit. And then Joel kept harping on this. He's basically like, we have all these different REPLs that are using Bootstrap ClojureScript, but they're all using their own code bases. And he's like, we all need to share a library that implements the common stuff. So fortunately, Andrea Ricciardi took all this, all the patterns and all the code, and kind of accumulated it all together in a nice library called REPL. So if you want to make a REPL for any reason, a Bootstrap REPL, I would highly recommend using REPL to do that, because it's basically got a lot of the hard work put into making, all the stuff you need to do to make a REPL. And if you think back to the beginning of this presentation, basically I showed how you could easily evaluate a form, and you can quickly make a REPL with just that stuff that was on that slide, really. But to truly make a REPL that just deals with all the corner cases and all the code loading things, you probably want to consider using something like REPL. And as a matter of fact, I think REPL even offers value, even if you aren't going to make truly a REPL. You just want to use Bootstrap ClojureScript. I think there's good stuff in there as well. And there's ClojureScript.io, which is a website that uses this library to make a web-based REPL, which I think is a pretty good one. And then outside of REPLs, I think there's some cool things going on. Because REPLs are just REPLs, right? There's this whole, now we have the capability to compile, and like, what else can you do, that would take advantage of that. So Nathan Sharvit's clips thing is pretty nice. It fundamentally, if you look at it, you could say it's kind of like a REPL, in the sense that it has a thing that you can type some code into it and evaluates it in a web page. But what it does is it kind of breaks it up into 4 separate boxes to show you what the compiled JavaScript looks like, and it kind of gives you some insight into what's going on. And he's also made it so that you can, I think this is part of the clips thing, where if you have a website that is like a blog post that is showing, talking about Clojure forms or ClojureScript forms, he's made it pretty easy to incorporate this Bootstrap ClojureScript stuff inside your web page, so that stuff that you're talking about in your blog post can become live, so that the reader can actually interact with the code if they want to. And then Chris Ford has Klangmeister, which is a cool, it's a music website. So essentially, you can type Clojure code into it that has like a DSL for describing musical phrases. My kids were actually having fun with this one. You can mess around and just make it play different notes. So it's cool in the sense that it requires compilation, right? Because you're typing in Clojure, but it's not a REPL. It's actually letting you type in some expressions that ultimately represent musical ideas, and it does that dynamically right there on the website. And then Quill had existed previously to all this stuff, and Nikita converted it over to Bootstrap fairly recently. And I think that roughly what that means is that I think previously it had to do the thing like Chimera had to do, which would be a callback to some backend service. I believe that's the way Quill was probably working. So now it can be self-contained. It basically just, I guess I didn't describe what Quill is. It's basically a, like Klangmeister was a DSL for making music. Quill is kind of like a DSL for making little graphical programs. So you can type in a little bit of Clojure and you get instant gratification. You see this graphical image that gets produced right there in your browser. And then another thing that we're using ClojureScript, Bootstrap ClojureScript for is to run the actual ClojureScript unit tests. And this helps make sure that Bootstrap ClojureScript is of high fidelity and that it's actually working. So it can actually execute all the Bootstrap or all the regular ClojureScript test suite, which it initially couldn't do. So it's kind of good that we have that coverage now, so we can make sure that Bootstrap itself won't regress. All right, so Planck, let's see. So Planck, actually, I'll show Replete real quick if I could. Let's see. So, sorry, I guess this presentation is going on pretty long now. I'll try to speed it up. So here's my iPhone. I don't know if you can see that. There's a larger portion of my screen. And Replete is it's this REPL that I was talking about that's on your iPhone. So it's running Bootstrap ClojureScript. And what I noticed, or at least what kind of struck me, was that this thing can start up pretty quickly, within, like, while the app is animating to launch, it's bringing up the engine and it's ready to go. And I was thinking, man, if it can run this fast on this low-end iOS device, what would happen if I took the same stuff and put it on a desktop? And that's what led to Planck. I basically said, okay, what, how fast can I make this thing run? So I basically took all the stuff that it was in Replete and essentially made it into a little desktop app. And Planck, fundamentally, I started off by basically making it so that it could do file I/O, things like, if you think about like Node has all these facilities to let you interact with the underlying operating system. So I basically started adding things like that into Planck so that you could call ClojureScript forms that would then ultimately interact with your operating system directly. So that's a very good question, and that's a completely valid approach. The answer to that is that I had personally been heavily involved in trying to get ClojureScript to run on iOS. I actually have an app in the App Store that's based on ClojureScript. And I had a lot of experience with JavaScript core, and I had built a REPL called Ambly that was based on all that. So me personally, I came from a background of knowing a lot about JavaScript core and having a lot of code that could interact with it. So that led to the least path of resistance for me to get Planck running. But then in hindsight, you're like, well, why don't you just do it with Node, right? And Ramsey Nasser has been working on a Node based REPL that's based on Bootstrapped as well. So that exists now. So I ultimately think that all of this stuff being on top of Node makes a whole lot more sense than what I've done with Planck, because Node is just a much huger ecosystem, right? But this is what I built. I built Planck, and it exists. Yeah. Okay. Yeah. Well, okay. So fundamentally, there's several ways to answer that. One of them is line itself is slow. So you have to factor out line. So don't like if you type line REPL, that takes 4 seconds or whatever, right? So don't do that. And if you instead just get the Clojure jar and you start up a REPL that way, that's pretty quick. It's like half a second or so. Whereas Planck might be maybe a quarter of a second. But then part of, you can say, well, why is that even the case? Why is Planck faster? I think it has a lot to do with just JavaScript environments optimizing for latency over throughput. Like JavaScript wants to start up quickly. It's designed to work in a web page, and it needs to launch now, right? That's its whole purpose in life. Whereas the JVM has become more of a server-side thing, and it wants to be more of a throughput thing. But in fact, there's a tweet that I sent out. You can look. I recorded a video where you can take the Clojure jar, and there's another trick that I'm playing with Planck where you can bring up a UI that is instant. You can get the UI live and going while other stuff is still being initialized. So you can actually make it so that the Clojure REPL is like instant, like a millisecond, it's up and running. And you could dig up a tweet that I did where I showed this is the case. And to do that, all you have to do is you have to rearrange the Clojure code to work that way, so that it shows the UI immediately. So I think of all those things, some of those are games that we're playing and different things, but fundamentally, the thing that's not going away or whatever is just the use case that JavaScript finds itself in. I mean, I think one part of what's going on is if you think about the core library, the core ClojureScript library, once you compile that to JavaScript, it's huge, and yet JavaScript core loads that thing instantly. And I think what it's doing, I'm not an expert at it, but I think what it's doing is it's probably avoiding parsing all of it. It's probably parsing the method functions and not it's delaying compiling things further until it needs to, and then it starts to jet the bits that are being used. So I think that's just a way of saying that JavaScript engines are optimized for latency. All right, so let's see a few more things. Planck supports class path, which I know sounds kind of weird because Planck's not a JVM-based thing, but I'm trying to make it so that it works well with the existing ecosystem. So you can pass it a class path, and it'll load ClojureScript libraries that are in jars, and you can require and load stuff from disk, and I'll give a demo of that. And then it has some kind of ergonomic nice things that I can show. So here's a picture of what it kind of looks like. Actually, I'll just show it though, because this is it's better to actually see it. Oh, this is kind of cool. FIP. This is an example of using FIP's ability to fold or wrap code at certain points. So I was messing around with in spec. You can now have you can have function specs appear as part of your doc string, and I was messing around with making those wrap with FIP. So there's some of the kind of cool stuff that I can do in Planck. I can experiment with crazy ideas, like trying to make it format things nicely. Things that if they pan out, maybe regular REPLs that would end up doing them as well. Here's an example of trying to make it run even faster. So this is just timing how quickly it can evaluate this expression, and that's like a quarter of a second. And then later on, I took the analysis cache, that gigantic thing, and I was analyzing what's making Planck take so long to even take a quarter of a second to do this. And I found that it was, loading in the entire analysis cache. And what I did was I took the analysis cache itself and broke it up into lots of little pieces, like different namespace sections, and made it put those behind lazy maps so that it would only load in the things that it needed as it needs it. And that got that down to like 0.155. So those are some of the examples where I was making Planck be faster than it really needs to be, just because it was fun to do, just to try to optimize it. So Derek was the guy who made Planck run in Homebrew. And if it weren't for him, Homebrew is awesome to get that thing delivered. So that's how I'm going to demo Planck. Let's see. So if you want to get Planck, It's real easy now. You just do that. I guess I already had it installed, but let's see. Okay, so what I want to demo real quickly is using this core async port. And I think this is just cool that this stuff actually works in core async. And here you can kind of sense that it takes a while to load this library because it's gigantic. Let me minimize this. So it's loading the macro namespace for core async. And it's still loading. So this is so David Nolan optimized this stuff. You know, he basically went through the reader and the compiler and analyzer, and he optimized Bootstrap ClojureScript so it could be as fast as he could get it to be. But even then, I think JVM ClojureScript is still a lot faster than Bootstrap ClojureScript. Because I don't think it takes this long to load core async if you're, you know, in regular ClojureScript. And this is kind of silly to have it take this long. But it actually works. I'll give a demo of that real quick. Create a channel, make a Go block, and then make a Go block that puts something on that channel and it actually reads it. So that's kind of cool. One thing I can show now, when I started Planck, I passed it a class path to this jar, but I also told it to write some analysis cache out. It made this directory here called Planck cache, and in there is a lot of the stuff that I was talking about, the analysis cache files, the compiled JavaScript, I think there's there's source mapping files in there as well. So all that stuff gets generated in cache, and that's part of what Bootstrap ClojureScript lets you do. When you tell it to load some code, it will compile it, and then when it tells you to evaluate it, it'll pass you some of these things, and you can opt to save them to disk, so that when you load them later on, you can pull them back in again. So if I do this again, I'll give the same demo again, but now this cache is in place. So now it loads that kind of much more quickly. Makes it more bearable in my opinion. So this caching stuff is kind of key if you want to make Planck scripts that actually consume large libraries like core async. You want to consider caching things. And then one other cool thing that I think was neat is this kind of illustrates the fact that it is Bootstrap and we have a val available to it. So Planck went ahead and defined an eval function, which you don't have in regular ClojureScript. So you can evaluate forms like that. And this is also kind of a mind-bending, interesting one. If you look at list of inc and 3, you can eval that as well. And that itself is normal. You can do that in Clojure, right? But what's a little mind-bending about this is that this ends up involving a function value that has to evaluate to itself deep down in there. So it's kind of an interesting technical twist. If you dig deep down into what it's really doing, there's a point in the ClojureScript compiler where it goes to emit that function value, and it can't do that because this regular ClojureScript doesn't today have any need to do such a thing. So I had to add an extra bit into Planck to have it handle that case. So that's some of the cool stuff with Planck. I guess a couple of other things I could show are, little things like if you're typing, it'll make the cursor hop back like that. Those are little cool ergonomic things. And I'm using FIP to help print things out and figure out what they are in color, syntax, highlight them, stuff like that. Just cool stuff. And parinfer is in there. So if you're typing, this is kind of an annoying thing, and to me in normal REPLs, if you hit return, it's now Planck uses parinfer to figure out where to put the cursor. So normally if you are used to regular ClojureScript REPLs, the cursor jumps to the very beginning of the line. So there's just kind of cool things that if you use things like parinfer and whatnot, you won't see these things in conventional regular ClojureScript REPLs, because they're just a little, I don't think things like par-infer are going to make it in there right away, but it takes, just experimenting with those things and proving that they have value before they can make it in there. So I think that's roughly what I wanted to show. Oh, there's a couple other things. I want to show Planck 2.0. It's running in Linux now. So Lucas Stadler helped do this. Sorry, my Linux locked up. All right, so yay, Planck 2.0 in Linux. So Lucas basically took all the Objective-C code that I wrote, and he ported it to C. And he offered it to me. I'm like, oh, wow. And I mean, it all wasn't there, but it was enough to get the thing running. So that's what Planck 2.0 is going to be based on, is Lucas's C-based port of all that Objective-C code that I wrote, which I think is great because it leads to the portability of Planck going to anywhere. And as a matter of fact, this is a picture of it running on Windows, and it's not actually running natively on Windows. It's running in the Linux shell on Windows. But ultimately, Planck theoretically could be ported to Windows itself. So I personally use Planck myself to generate the Planck manual. I use the Markdown CLJ library, and I use it to deploy these websites, my blog and stuff like that. Planck actually, interestingly, uses itself to compile its own macros. You can imagine if you don't do that when you load a macro namespace on Planck, it would go ahead and compile it on the fly. But Planck, in its game of trying to be really fast, AOT compiles everything and carries those AOT artifacts with itself. So that's roughly some examples of Planck using itself. And then that's roughly it. I think the future in my mind of Planck is to port it to the Atari 2600, and then I'll be happy.